Hi, everyone. Welcome to Farming Fast and Slow. My name is Adam Wolf here from Arable Labs, and this is a podcast that tries to join two people, numbers people who want to know more about plants and weather, and plant people who want to know more about numbers and code. Just a little bit of housekeeping to start. There'll be a time at the end when you can write in questions. Zoom has a Q&A feature. These are all posted afterwards on YouTube, and so you can subscribe if you want, or otherwise use this as an opportunity to save it for later if you wanted to watch. And of course, we've got a bunch of upcoming shows as well. And so we've got some plans around rain, frost, spectroscopy. And if you have any ideas, we'd love to hear them in the comment section. So today's topic is understanding crop growth stages. And, you know, I have this idea around, you notice that many farmers tend to specialize. If you grow broccoli, you're pretty consistently a broccoli farmer and you don't switch to tomatoes. If you're growing tomatoes, you probably grow a lot of tomatoes. And so agriculture tends to reward specialists. And I've tended to think that that's because a lot of the talent that comes to farming is around understanding the peculiar biology of the plant that you're growing. And that comes down to this idea of hot moments, that there's particular phenological stages like flowering or harvest that require skill and, how to navigate the rapids of, weather, because often those moments, those sensitive moments coincide with risk for rain right before harvest or frost during early bud break. And so that's why we wanted to create a show around crop phenology, crop growth stages, and how they show up in kind of model world and the real world. So with me is Jess Bollinger.
Hey everyone, I'm happy to be back for the second episode of the webinar. Based on some of the feedback we got last week, we were going to structure this a little bit more. It will still be a conversation, but in terms of what we plan to cover today, we'll go over the concept of growth stages. As Adam mentioned, why are they important? How do growers and researchers identify different growth stages and growth stage transitions? Adam is going to give a little bit of background and a sneak peek at how we are predicting growth stages at Arable. We'll talk a little bit about what we think are the most exciting growth stages, and then, as Adam mentioned, a little deeper dive into aspects of weather at different growth stages, and then how we can respond with different interventions in the field to change outcomes at the end of the season. So let me stop sharing. So I thought, Adam, it would be helpful to get an understanding of what are growth stages. And all plants are different, but is there a basic way that, someone new to this could be thinking about what happens from emergence to the vegetative stage to the reproductive stage and what's happening with the plant?
I think of growth stages as kind of like the demographics of a crop. So, you can count all kinds of things continuously, like your age, your height, your weight, but then, some forms you have to check mark. Are you single? Are you married? Are you married filing separately? Are you divorced? We fit into these categories. And, if we think about, we're these biological organisms, we're born, we go through a juvenile stage, we, pass through puberty, we're a reproductive stage. we're having offspring, and then we stop, and then you know, we don't really senesce, but we're after the reproductive period, and of course we die. And you know, those categories are functionally distinct, and they're different from, you know, growing in terms of height or weight. You know, so my transition from, you know, a juvenile into reproductive doesn't matter how much I ate as a teenager, right? It just depends on like the progress of the biological clock. And so crops have these biological clocks that transition them from, you know, germination to emergence to juvenile. They're putting on a bunch of new leaves. They're maybe growing in height. And then, you know, they start to put out flowers. They flowers get pollinated. They're growing fruit. And so these are kind of major life transitions where they're switching from, you know, stage 1 to stage 2. And then, you know, we usually harvest them at some particular stage. And so it's important to keep track of what these stages are in, because they totally define how the crops are managed.
And then similar with humans, there are different risks that happen at different stages. And this is very morbid, but I was looking at, you know, the percentage of deaths associated at different life stages. And there's just different things that people are doing. You know, when you're 16, you get your driver's license. So there's more risk of getting in a car accident at that stage versus things that will affect you later in life. And we were talking about, you know, the pandemic that's happening right now and how, you know, it skews towards a certain age demographic, and that there are things that growers can be thinking about at different stages that are just relevant for that stage.
Absolutely. The risks are different. And, you know, how much has been invested already versus what could be invested in the future also changes, you know. So if we think about, gosh, at some point early in a wheat plant's growth, it sends up a different number of tillers. If the conditions were bad at that moment, that absolutely changes the whole kind of yield potential trajectory, and will change, you know, is it worth investing a lot in this crop in the future?
I thought, you know, we're talking about growth stages and, you know, the different transitions between growth stages in a crop's life. I thought it could be helpful to give a little bit of overview of some of the process that's happening and driven by the sun, and then how we are using measurements of the sunlight and the absorbed and reflected light from the canopy to measure and quantify growth stages. And I drew some pretty silly diagrams this weekend, but I thought I could share them to hopefully help people that are not doing this day to day think about some of the more complex topics that Adam's explaining. So you can see here, Adam, I drew the sun, and then what's probably not completely accurate, but conceptually how I think of, you know, light hitting the plant, thermal energy, and then different wavelengths of sunlight either being reflected off the ground and hitting the canopy, or bouncing off the canopy and being reflected back into the atmosphere.
Yeah, and this ties into this idea that, you know, growth stages are something you could go out and look at. You can count the leaves, you can, you know, pry open the kernels and examine them. But for the most part, really knowing the exact growth stage means you're showing up in the field. And as we all know, that is, it's hard to do practically because agriculture is everywhere. And so we've come up with a lot of different ways to develop proxies that are related to the growth stage. And so the thermal is one kind of biological clock that we could be measuring. The light is a different kind of biological clock. And then this reflected light is less a biological clock than a different way to measure it that doesn't use your eyes, you know?
And for every, is each each crop type is different in terms of when it progresses, when we think of growing degree day units to the next stage. But then even within crop types, different varieties are going to move differently depending on how they're bred or how the hybrids are I guess, released.
I mean, absolutely. And a lot of, breeding has gone into localizing the genetics. And I don't know if people read Guns, Germs, and Steel anymore, but this is kind of Jared Diamond's argument. Why did civilization progress differently at like mid-latitudes versus in the southern hemispheres? You have a lot of horizontal territory for which, let's say, the photo period is identical because it's based on latitude. And so a lot of crops that were historically in their wild relatives tuned into sunlight to choose when to flower, those are really kind of latitudinally oriented.
I'm just sharing one of the other diagrams I drew, which is a very rudimentary explanation of growing degree days. But my understanding of it is that as energy from the sun heats up the plants, that there is metabolism that occurs within them and that they're generating biomass. And there's this perfect temperature or period where the photosynthesis is happening at a certain rate that causes the maturity in the plants. And so here I tried to draw, what I see as believed 50 and 86 degrees, and then what it looks like the growing degree day pattern that we see where the crop emerges, and then it grows pretty quickly. It slows down a little bit in the flowering, and then the brown at the top is the senescence at the end. And I, was wondering, if you could explain in more scientific terms a little bit what's happening with the plants at the different stages.
Well, so here, let's say these degree days, the slope of that line over the course of the calendar days doesn't depend on the variety.
Okay.
So the amount of heat that's experienced, and it's thought, that temperature drives the rate of metabolic processes, cellular division, all that type of thing. But, what changes is, those vertical stripes when those different stages happen. And so an early maturing variety, might have all of those stages stacked up on the left. And so it is harvested instead of October, it's harvested in September. Maybe a late maturing variety, it's stretched out the other way. So I think of this almost as if we've got, calendar time follows this kind of linear scale. Thermal time, it's sort of stretched out when it's cold, so time progresses more slowly, and then it shows up, it's stacked up much more quickly in the summer when it warms, and then in the fall, it cools down again, so things stretch out. So if we think about what does that do to growth, over calendar time, it might progress slowly, but if we put this into degree day units, it really accelerates the time and slows it at other times. So I think of the degree days, concept is, stretching and contracting time as relates to these growth stages.
Got it. And so I feel like, we talked about this a little bit with the Madagascar corn and how it's a different time than we would expect than corn grown in Nebraska. And can you explain, I guess I'm forgetting what was happening there with the corn?
The Madagascar corn is interesting. It's a lot warmer at night. and so it's metabolizing a lot of the sugar that it's developing. So it gains a certain amount in the day and it loses it at respiration. In the Midwest, it's cooler at night, and so most of the photosynthesis that it captures in the day it gets to keep at night. And so that kind of stretches out that maturation period of the kernels. And so this shows up even in grape production, famously in wine grapes, but especially keen in table grapes, where the Brix accumulation it really drives the timing of harvest. So maturity is defined at a certain sugar content. So if it's warmer at night, it is taking longer to reach that next increment of maturity because it's all kind of respiring. So it's another way to think about this progress is the carbon balance of the plant. In addition to that, we've got these discrete growth stages, like is there fruit, is there flowers, yes or no. And then harvest often has these quantitative aspects where it's mature if the grain reaches a certain moisture content, it's mature if the fruit reaches a certain sugar content. And those have kind of different models.
The size and the quality for those two things, right? So it's like both coming together at the same time.
Yes.
Okay. My next drawing I did was really about the light intensity at different times of the year. And so what was always fascinating to me is how if you go to Canada and you go in July or August and you see all the canola fields, and my understanding of why they grow so much canola in Canada is because it has to have a certain day length, and that at that latitude, the day length is long enough to go through fairly quickly the whole process of canola maturation, even though the temperature might be less good for other crops.
Yeah, I mean, it is a small grain, so it lends itself to those short seasons, but it's one of a few different crop plants, legumes especially, that they haven't really bred out the day length dependence of its phenology. So, some crops you might plant, corn may have no day length sensitivity to it. So when you plant it, you're just counting up degree days, and you can pretty well predict when the harvest is going to happen. But
wait, can I ask, are they breeding it out of plants?
Oh yeah, for sure. I mean, it poses an annoying limitation if you think about it. So if you are a seed breeder, you would wish for the greatest possible market for a given variety. And if you remove the day length dependence, that opens up kind of new territories for it to be able to plant it in. It doesn't totally get you out of trouble though, because different latitudes just fundamentally have different season lengths. So let's say in the American South, you can plant earlier, the season is potentially quite a bit longer, and as you move north, it's getting correspondingly shorter and shorter. The time in between kind of last frost and first frost.
Got it. And so I guess, if you just think about it, the sun is doing the same thing year over year. Can't you just look at what is the solar intensity at one spot on the earth for that day, and what is the sunrise and what is the sunset, and just do some math and put together an equation or an integral to understand when that crop is going to be ready, if it's driven by the sunlight, or why is that more complicated, or why do we make it more complicated?
I mean, the day length is Absolutely. You can look up what the day length is going to be in the year, 2058 or whatever you want to, like we understand how the sun or the earth orbits the sun pretty well. But, there's some aspects of it where, let's say the onset of the spring rains just sort of delays the warming up of the ground, maybe, the cloudiness in the sky. So the actual, uh, progress of thermal time is different every year. And this, what you're pointing to is this daily light integral. It has tended to be that people working in outdoor crops are working in thermal time, maybe with a little modifier for day length. People growing indoors tend to use this daily light integral to plan out the maturity timing. So if you're growing, cut flowers, hemp, other kind of indoor crops, this is where, they maintain a constant temperature more or less, but being able to understand what the sun is providing really alters the rate of maturity. And, one of the levers is really being able to supplement what the sun isn't providing or just manage around it in terms of, managing your contracts to deliver earlier or later.
Got it. So that's when you think about predicting it, you're essentially just moving along the curve to understand what the solar radiation is, what the incidence of cloud cover is at different times, and you can start to move towards what is the timing going to be of the crop being ready, and then backpedal that to set contracts.
Yeah, and I mean, I think of let's say we make a plan for the business, what our cash flow is going to be into the future, and if we have a hire that we're making that doesn't start for another month, then the whole cash flow is kind of a little bit flatter, or they come on early, so the cash flow is a little bit steeper, and so the actuals are just slightly different from the predicted. And people who wear green visors care about such things, but it's sort of fundamental to meeting contracts, to be able to know, like, obviously supply chain is in the news now, being able to rigorously account for these environmental effects is really critical to being able to make your promises.
Got it. And so I wanted to share a little bit about, the project that we were working on with the USDA, and Laura Lee Corenza on our team, did a lot with modeling growth stages a third way, which you shared a little bit earlier, looking at the NDVI by the growing degree days. And I think it does a good job of explaining, what you were sharing about thermal time, and then the plant's response to what the expected growth stage change would be, and then what actually happened. So first I was going to show quickly, sorry, one sec.
And while you're teeing that up, I have to say it's one of my great annoyances as a crop modeler. Some of the work that I did at UC Davis, I don't know, like quite a long time ago, involved modeling, experiments, and you really had to know the exact variety that was being planted in order to be able to, make, to reproduce the observed data. And fundamentally, some varieties are shorter season and some varieties are longer season. And so it's all well and good to imagine that we've got like this thermal model, but in reality, varieties are changing so often. The lifespan of a hybrid is on average maybe 5 years. And so what are we supposed to do? to keep track of these kind of thermal requirements to make predictions if the genetics are always changing. And this is where we got really excited to be able to use this sort of infield measure of canopy cover to track the growth stages without having to rely on the thermal time.
Right. And I think it's so cool because, you read all this literature and it tells you, at 600 growing degree days, you're going to have the flowering process begin, and it's hard to understand, when you read the academic literature and then what actually happens in the field. And so I think what's really cool when you can model both of them side by side is that you can see, what was the predicted stage change for each of these, and then what really occurred in the field. And these are, in processing tomatoes. And one of the challenging things about processing tomatoes is irrigation and ensuring that you're keeping them well watered in the beginning and then dialing it back at a certain growth stage in order to drive up the soluble solid content, because they're more valuable than when they're contracted at the market. And so you can see across these plots that we ran over last summer that there's this dip between the vegetative and the reproductive stages, and that the ability to be able to predict when this dip is going to happen or when peak NDVI is occurring gives folks managing irrigation scheduling some insight into, what they should be doing, how much they should be pulling back at different times in order to change the outcomes of the crops. And I drew this picture, Adam. And
I can't wait.
Oh no, did I take it out? Oh no, maybe it's before this. And it is showing my interpretation of what's happening with the spectrometer and how it's measuring the plant response of the light in the canopy, and the different stages as they're changing on the plant.
Sure. I mean, it's so what you're showing is the NDVI growth. And, at planting, it is growing slowly. And on that up curve, it's stacking on more leaves. And then somewhere around the middle of that curve, it is expanding the leaves that it has. And then it reaches a plateau where it's got all the leaves that it needs. And then it is sort of investing the products of photosynthesis into growing the mature fruit. And so I think you had these growth stages labeled on the next graph, where it switches from being green fruit to red fruit. And it's interesting, you see more or less the same phenomenon if you look at wine grape NDVI curves, that it is reaching a kind of a peak in leaf area, and that tells the plant that it's about time to transition. And in both these processing tomatoes and wine grapes, the growers actually nudge along the plant's signals by pulling back on the water, which gives kind of a further acceleration towards the development of the kind of maturing of the fruit at the expense of the canopy. So it's really, I think, exciting to see that we've got a way to parameterize the growth stages using something that we can measure from afar, as opposed to, drawing on some publication that was put out years ago, probably on a variety that is not relevant to us.
And the color, the spectral color that as the curve moves, we usually think about it as 0 is bare earth, and full green canopy is 1, the ratio from 0 to 1. And so is it that the plant is losing greenness, or that the color of the flowering at that transition is just overpowering the green that is being picked up by our device or any type of spectrometer?
It's an interesting question, because you see this decline again, not only in processing tomatoes, but also in the wine grapes. I think because it's transitioning towards reproduction, that comes as an expense to the canopy. So to some extent, the leaves are, they're photosynthesizing and providing, all the sugar that is going to be used to grow the fruit. On another level, though, it is a storage organ, so it's storing all this, nitrogen and other micronutrients that are going to get translocated into the fruit in order to develop. And I mean, this is kind of a funny anecdote, but when I was in Kazakhstan, I was like admonishing these women that I was living with because they were sucking on lemons, and bear in mind that they had, like, for the most part, gold teeth. And I was like, oh my God, your teeth are so terrible. You can't just be like pouring sugar on lemons and chewing on them. And they said, no, you don't understand. We all lose our teeth when our babies are being born, like when we're pregnant, because the body is actually stealing the calcium from the teeth to grow a gestating child, so, and they, eat the lemons for vitamin C. But, the growth of progeny comes at the expense of the mother, and so I think when you see these kind of declines, you see it in grain plants too, like pre-senescence. There's a whole period when it's continuing to grow the grain at the expense of the leaves, and you can see it in the NDVI. Another sort of facet of interpretation is that loss of NDVI doesn't necessarily mean loss of leaves, because the NDVI, the red part of the NDVI, is sensitive to the chlorophyll content. And so it's a so-called green leaf area. And so loss of greenness shows up in this decline of NDVI.
Even though the overall vegetation or the overall crop cover might not change, it's just a transition between the colors, or what the spectrometer is perceiving as the reflected light off the canopy.
Yeah. And so for me, what's interesting is, we've got this curve, and we can start to annotate parts of it. Like, this is concave up, this is concave down, this is NDVI reaches its halfway point, now it's at its peak, now it's plateaued, now it's going down. And by being able to annotate it, we can tie those into growth stages, and now we've talked with researchers at UC Davis that this phenomenon with the processing tomatoes is a real thing, to see that dip right at that transition to fruit reddening. And I think that we'll start to see other crops where we can kind of tag their phenological stages. Let's picture canola is like obviously bright yellow. We should be able to mark the timing of flowering, and then, retrospectively see, well, what was the weather like during flowering? Is this going to be a good year? So almost real time, handicapping.
Well, it's also just, as we do it over and over again, the more data that feeds into that model of X happened and then Y happened, we start to see, like, understand the exact peak NDVI period that is the precursor to that flowering, so that the next season it's, flags it and says, this is what's about to happen next, is how I think of it.
Yeah, absolutely. And I think there's going to be parts where, I mean, this has always intrigued me in the series maze model, which weirdly I have, like, my textbook next to me with it actually comes with a floppy disk in it. There's a certain growth stage where it's still on the upward growth trajectory, but the photosynthesis during that period corresponds to the number of kernels on a cob. and that is like 85% of the yield potential of the corn plant. So, then we're looking at, well, how steep is the growth in that period is going to predict, end stage yield potential. And yet, right now, the number of, data sets that are measuring, rate of change of canopy or photosynthesis in that period. So it'd be, light times that canopy cover. Those data sets don't exist. And so we have a real opportunity to learn a lot in the next, set of growing seasons on that.
Yeah, I think you hit what I was hoping you could talk about, which is, your favorite growth stage. For me, mine is flag leaf stage, because I think, well, it's really cool when you see the field and the little flags, waving for the wheat crop in the field, and you understand how they came up with that name. But then also the concept of how the flag leaf, when it pops out, and based on whether it has, fungal diseases on it or whatnot, there's some determination of how big or how much yield is going to come from that plant. And I know you talked a little bit about that with corn, but I was wondering if you could share more about how the plants determine progeny and the kernel count per row, and what is the biological process behind that?
I mean, it's interesting, and there is sort of like an evolutionary biology perspective on this, where there's this question of reproductive fitness. And so if a seed is not fit, then it's useless, and so knowing that it's this binary condition, it's fit or it's non-fit, then it's a bad idea as the parent to raise a large number of marginally fit offspring. Mm-hmm. Instead, the mother aborts a certain number of the progeny in order to have a smaller number of highly viable offspring. And so that depends on the carbon balance. So let's say for permanent crops, a lot of that carbon balance is stored from the previous season. Even after the harvest, it's stocking up on, non-structural carbohydrates that it's keeping in the roots. And those are what, signals to the, the mother in the springtime during fruit set, how many offspring can I bear? Right? And so if it's in a marginal carbon balance at that early spring, it doesn't matter what happens after that. Those fruits have already been lost. And so a lot of people are looking at how do we, increase the yields of some of these crops that, are frankly barely domesticated. Compared to a wheat crop, many perennials are just like practically wild. And, I think we're learning a lot now in terms of intensification, fall irrigation and fertilization, things that are allowing for, a favorable carbon balance during these particular moments.
I mean, I feel like so fascinating to me, the idea that you could, as a parent, come up at a certain stage and make this assumption about how much progeny can I take care of, or what's my offspring's life going to be like, and then just choose the number based on some optimized outcome that the plant can sense for the upcoming season.
I mean, it's like, but as humans, we do that all the time. I mean, there's a lot of, I don't know, going back to my time in Kazakhstan, the reproductive rate was like nothing.
But I would argue,
so the pessimism about the future was dramatic.
But I feel like the opposite, because I think for so long humans think of offspring as almost a workforce, and it's changed recently that we no longer see it that way.
Yeah, like well, and perhaps some risk mitigation,
Yeah.
you know. But there's, I mean, there's different strategies in plants, you know, for, you know, fruit trees have a relatively small number of, you know, offspring that they'd put a huge investment into, you know, and down if you go into, I don't know, thistles, you know, there's just like an unbelievably large number of offspring that individually have like virtually no chance of reproducing. And, you know, as a species, we are, you know, relatively few in number, and we put a lot of investment into our children. Um, but, you know, some of this, you know, thinking is, I don't know, developing an intuition about the life history strategy of a plant. Like, what does it want to do in order to uh, uh, survive? On the one hand, breeding has tried to convince plants not to obey its kind of genetic program, like breeding out
Mhm.
competition between neighbors. But nevertheless, on this sort of, you know, fruit set and, you know, yield, there's a lot of crops that have, you know, barely been selected for or managed for in that regard.
We have probably about 6 or 7 questions that came in from the audience. Adam, is it? I'm just going to transition over to reading some of
Yeah,
them.
yeah, you be the boss.
Does the GDD calculation change in perennial crops versus seasonal crops?
So one thing that changes across all crops is like the temperature bounds. So even within, let's say, wheat has a lower base temperature, you know, it's found at higher latitudes, versus corn has a higher base temperature. So wheat might be, you know, 5 degrees C, whereas corn might be 10 degrees C. But then between annuals and perennials, perennials often have a like a wintertime requirement, and so they go through some sort of vernalization period or cold period where they have to accumulate like negative heat units or cold units in order to transition growth stages. And then once its cold requirements have been fulfilled, it switches into heat units. And so this is kind of one of the wrinkles in perennial crops. Now, I say that as a, you know, having a temperate bias because I always lived in North America. If you move into the tropics, there's a lot of crops that don't have this kind of cold warm transition requirement so much as a dry wet requirement. So like cocoa, coffee, black pepper, you know, have these like they accumulate, let's call it desiccation units,
Okay.
and then the rain comes. And in a sense, it's, you know, where day length in some of these annual crops triggers, you know, flowering. This is a way for the plant to be synchronized with, you know, evolutionarily the timing of the seasons. And so, you know, having a cold clock helps it adjust to the timing of spring, or a dry clock adjust to the timing of the monsoon rains.
Got it. So that's why in coffee, they're always trying to time the precipitation events with the flowering event because it leads to some quality or yield outcomes at the end of the season.
Totally. And coffee is really interesting because it is grown across a lot of different locales, some of which are favorable like all year long. And so it doesn't have this seasonality. And others that have these pronounced wet and dry seasons, which have like these heavy synchronization. And one of the casualties of uh, climate change is really the loss of that synchronization. You know, so one risk might be that, you know, you're growing in a place and it just doesn't get cold anymore. well, that poses a challenge, obviously. But it could be that it gets cold, but not real cold. And so the different parts of an orchard are, not synchronized well with each other. And so the harvest becomes more sloppy because the flowering is not as well synchronized. So that also kind of poses a risk in the tropics with these kind of dry, wet transitions.
So I guess my question though about climate change is, we were talking about the corn in Madagascar. Is that ultimately what ends up happening in more temperate corn growing regions where it takes, because there isn't that cool period at night where it extends longer to produce the same crop? Or am I getting that wrong?
No, I think it absolutely is going to play a role. It's one of the, I don't know, most prominent findings of climate change research is that the cold temperatures, be it winter or night, are changing, increasing more quickly than the warm temperatures. So the max, I mean, we obviously have, more heat spikes and record hot days, but in general, the average tends to be that the nights are getting warmer and the winters are getting warmer. So if you just take the nighttime condition, that means it's harder to accumulate, all the photosynthesis in order to mature. And so some of the, biggest yields are found in places that have a lot of sun during the day and it's really cold at night. So everything that was photosynthesized is retained, so that nighttime warmth is like a tax. And taxes are increasing. So I guess the short way to put it.
We had a question come in. I showed the graphs of the NDVI by GDD, and someone from the audience is asking if it was taken with a drone, and then another person asked, how does Arable measure these different growth stages? And so I wanted to explain quickly that we have, our device sits above the plant in the field, and it's getting the temperature, the solar radiation, and the NDVI. And so that's all coming into the system every 5 minutes for the measurements, and then we're delivering an hourly average. And that allows us to look at these 3 different ways of understanding the exact status of the plant. And overlaying it with weather so that you get the combination of both in terms of how you make management decisions. Adam, do you want to talk a little bit about the difference between some of what you get from spectral data from satellites and drones and the thermal data? I know there's, when we look at these 2 data sets, there's some big differences, but why, when you founded this company, why do it in the field? Why use
I guess, to keep it concise, I think that there's, this idea that's the difference between a point and a grid. So this room, if we measure the temperature, right above my keyboard, it's pretty warm. If I go over by the window, it's cold. If I go to the other end of the room, it's kind of stuffy. And so there's a lot of variation, and yet there's only one thermostat here. So we get one temperature number. And in some circumstances, that deviation matters. Imagine instead of, one thermostat, actually, we don't even have a thermostat in this room, it's downstairs. And so it's totally insensitive to this room. In fact, it's always wrong, for me and my, comfort. And if you think about, gridded weather, for example, as a source for the temperature data, there's a lot of contours that, it could be due to hills and mountains, sun hits on the south side versus the north side. There's contours where the air is flowing at night and during the day, altitude. So all those things are basically absent from the grid. But the point, like that ground measurement, sort of sees that texture, and kind of the same phenomenon is at play with the satellites, which are, they've got a view, but there's a lot of missing data points, and so the let's say, and they're missing because there's clouds or it's not overhead at all. So the phenomena that we're talking about, which is like looking at the rate of change of this curve, are just, you don't get to see them with a satellite. And so fundamentally we like this this idea of hot moments instead of hot spots, where a satellite can find a place that's bad, where this is kind of taking, it's has a narrative arc. There's a beginning and a middle and an end, rather than just a scene taken out of context. And so that narrative arc, the characters of temperature are going to come into a play. Light, we can measure the canopy, its stress, all those things are going to have kind of an accumulated impact on what the outcome is. You can't just take a snapshot.
Got it. And then I feel if you're trying to do anything predictive, you want to have the best data to feed into that model, to remove the noise, and to actually be able to have a precise determination of the event that you're trying to predict.
Well, and I might say, images are good for predicting where. Mm-hmm. Like, where might you go check for water stress? Where might you go look for disease? Where might you see if your water main is broken? Where might you sample for nitrogen? So there's all kinds of great where questions. But, I think of agriculture as played out in time and navigating, when questions or if questions, like when is harvest going to be? Obviously, there's a bunch of kind of labor issues, supply chain issues, kind of get the equipment issues. Is it going to rain before I harvest? All these when questions that are inaccessible to you with a map.
Got it. So if you're trying to plan, well, I always think about it, if you're going to take an action in the field, like spray timing, and you want to know, I'm going to spray my soybeans at R3 or in wheat GS30, the ability to know the weather and exactly when that stage is going to happen, it becomes a when question, and probably also a little bit of a where.
Yeah, lining up the time and seeing like, gosh, these two things seem to be converging in a bad way.
Got it. We're about 7 minutes over, Adam. So I was, probably going to have to wrap it up. I'm not sure of the topic for the next one, but I think you're having a guest on the show next time.
I'm hoping that we can talk about frost. I had to convince some of my own team that frost is interesting, but frost is 100% fascinating. And the way it plays out in different geographies and different crops is itself kind of interesting, and it ties in with our kind of growth stage issues, because there's plenty of times when frost is irrelevant. You're expecting it's going to be below zero for some part of the year. Anyhow, so I'm hoping that we're going to have a guest on to talk about the kind of deep story of frost. Otherwise, it's me talking about meteorology, which is not uninteresting, but I'd love to have more, facts on the ground.
Very cool. Well, thanks, Adam, for your time and for having me on the show again.
Oh, I always enjoy it, Jess. Thank you.